Testing. Testing. Yeah.
That's fine putting it here, or should it be closer?
That's fine.
Yeah. Testing. Hello? Hello?
So it's not amplifying, it's just for people.
Okay, okay, yeah. Thank you.
Thanks. And just let me know.
Thank you. Yeah, they're pretty good here. Yeah. In the past couple of years, they integrated all this stuff, and I think it usually works pretty well.
Yeah. Yeah. It's very nice.
Usually, no one actually joins on.
But so then I can put, or maybe I don't know. It's needed for this recording. Whoever watches it recording.
I would still
do. Yeah.
Because I think they do put them on YouTube, and it's actually not too bad. You know, if you for being on the job market, if there's a good talk, then you can make it. Usually I mean, also like if you turn off my phone, I'll come back up and be like,
Okay, so better not do it. And did you already organize some thematic semester here at Institute?
no, I don't have any desire to do so.
Okay.
To be honest, it's like it's more work than you know. I think it's just a pain, but even like organize a conference, I think it's more trouble than it's actually worth. There seems to be no shortage of conferences, so
No. No.
they did have like a probability one last in the spring, which was really good. So they had like a lot of good speakers doing like mini courses, things like that. So that was nice.
So this means it's more targeted to younger people like PhDs.
No, I think it sort of depends on what the organizers want to do. You know, they also like offer courses through the Fields Institute as well. So you can like teach your course here, for example. I think it's also broadcast.
Should also. Sorry, I still also need to write something down, so maybe I should clean the whiteboard a bit. No.
Other way on. All right. I'm taking an exam right after, so. This is Jeremy Costel.
Hi, I'm Yosha. Nice to meet you.
Is 370 this semester? Yeah, and 377. So how's 370 turning out? It's okay. I mean, I'm to use direct book and just. Does he have another graduate book? Yeah. I didn't know that. I don't like his graduate book very much. So. Oh, I like his graduate. But I don't think he's very organized. To put it mildly. But the thing is, though, he does a lot of good topics in it. You can't really find another book with the right topics. It's always been a problem. But the undergraduate one's just that. Oh, yeah. So. Are there mistakes, or it's just like, you know, why stuff is in the order? Well, there's endless mistakes, they're not stupid typos, but no, he just doesn't. Our undergraduates are better than the bug. That's like. So. We're basically finished all the material very quickly. He's got too many Adobe problems, which are just all the same. How many problems do you want to give them? I would learn with 6 white balls and 2 green balls. You turn it upside down and it's like. It's a problem we have it off schedule. Yeah. Okay, sometimes you just can't help. I have a question. Top eigenvalue. Yeah, GOE. Yeah. So if you have a top eigenvalue of GOE. Yeah. And you look at its distribution, finite head. Yeah. There's already a differential equation for it. Sure, yeah. Or if you take, here it is. If you take the log of the probability distribution, it's already a differential. I don't know if it's true for the GOE. Because it's also one for L. Oh, so then, yeah. Definitely. What's that? Probably. But I don't know. For GOE. If you say there's one for like area ensemble. Yeah, that's my. I don't see how there could be one for the. Right? Okay, I just wondered if you've never seen one. I don't know. I've never read it.
Hello. Hi. Hi.
Hi. This kid from the class. I didn't like this. It's less than history started, right? Yeah. Because for a long time. But there's less blackboards. Yeah, the blackboard is the best. Whatever. You know history. But it was like so it's not that expensive. Oh, yeah. I think it's a lot. Yeah, it's a lot. We're like people so bored. It's a Tuesday night.
This is part of our. Yeah, exactly. You could even sell.
Are you ready?
Yes,
Sorry.
sure.
I'm gonna go this. You can take about 3, I guess, maybe end a little bit, like 3, just for questions.
Okay. Yeah.
All right, thanks so much. Thank you everyone for coming today. Next week, we're back at the usual schedule. 3 o'clock on Monday. But I'm delighted to introduce Josh from IST Austria, and he'll tell us about the Zigzag strategy for random matrices.
Thanks, Ben, for the introduction, and thanks to all the organizers, I guess, for the invitation. Thanks for having me here. I will report about some joint papers, survey them, kind of they are subsumized under this strategy, the Zigzag strategy, which I will also tell you about. And all I tell you is joined with this list of people here below, out of which Laszlo Erdős is my advisor at IST, and the others are former or current group members. Okay. So let me wait maybe first before others entered, and then start gently by introducing kind of the standard random matrix ensemble, which is kind of the predominant one which you can keep in mind throughout this talk. The Wigner matrices, which in particular include the GUE or GOE matrices. They somehow were introduced by Wigner in the 1950s with this vision in mind that eigenvalues of random matrices model energy levels of large complex quantum systems, and in some sense should have some universal flavor in them. They're defined as follows. You take this big matrix W of size n times n, n is the large parameter in this business, and it is as IID as possible, you could think of. So the Wij are centered IID random variables up to the symmetry constraint that you have real spectrum. We also, kind of for technical reasons, so okay, we assume them to be centered, so we expect probably the center of the middle of the spectrum be around 0 then. We also somehow assume for normalization that the variances are exactly 1 over n. This will just ensure that as the size of the matrix goes off to infinity, it neither shrinks down to 0 or blows up to infinity. And for technical reasons, we also put this, here it works, this moment condition that when you scale them up by square root of n, that all moments are finite. This is a different ball game talking about kind of what happens when these moments are not finite. So let's assume this for this talk. Let me denote the eigenvalues of this random matrix by lambda 1 to lambda n in this ordered fashion. So lambda n is the biggest, lambda 1 the smallest. And somehow in this vision of Wigner around this question, you could ask different questions about these eigenvalues on different scales, so to say. So this first picture tells you already one kind of universality result. Namely, that if you just sample all these eigenvalues, you look at all n of them, then you will always find, independent of which precise distribution you put on the entries of your random matrix, you can flip a coin or you can put a Gaussian or whatever. You always find the semicircle law as the density of states in physics terms. Then you could also ask questions not about order n many of these eigenvalues, but say order n to the a for some a between 0 and 1. Then you could think of mesoscopic questions if this was a macroscopic question. And you can also ask very fine questions, which look at the individual eigenvalue. And this was mostly what was this vision about, that namely the gaps between the eigenvalues, which is what a physicist can measure in his lab, are universal. And this is here, this graph below. The Wigner surmise is the black curve plotted here, and green is the histogram of the eigenvalue gaps. So as I told you, kind of you expect these n many points to be inside a box of order 1. So when you scale it properly up, kind of that you get order 1 random variables. When you look at the consecutive difference of lambda I plus 1 minus lambda I, it's a positive number by definition of these quantities. You will see this profile roughly emerging. And one feature of this, which is kind of also characteristic for the chaotic quantum systems, which it should model, is that it is very unlikely to find two neighboring eigenvalues very, very close to each other. So they repel each other, which is in contrast to systems which you could call integrable, where the eigenvalues don't repel each other, and you more see a Poisson distribution of these gaps. Okay. So asking about eigenvalues, it is convenient to
say Wigner surmise, it's important to say that that's wrong.
Hmm?
The Wigner surmise is wrong.
Yes, yeah. Yes, it is an approximation to the precise curve. So yeah, but it's easier to write down this surmise. Exactly. So studying the eigenvalues, it is very convenient to look at the resolvent of the random matrix. Okay, what we're actually interested in is kind of this random measure. I take the sum of delta functions centered at the random location of the eigenvalues, take 1/n, so it's a probability measure, and I want to understand how this behaves. And it's convenient to do this via its Stieltjes transform or by the resolvent of the random matrix. So what I do, I take the Stieltjes transform of this measure, which is exactly, just by definition, 1/n times the sum over all the eigenvalues, lambda I minus z. And this is also identically equal to the normalized trace. This is what I would denote by these Langle brackets of the random matrix. Okay. Estimating a resolvent very naively, you could just do it by saying, okay, it is bounded by 1 over the imaginary part in absolute value of the spectral parameter. This is, I mean, when you just look at the operator norm and you look at kind of a z, which is exactly the eigenvalue, the real part which is matching the eigenvalue, that's the truth. But this is not kind of the correct topology to understand these resolvents. Namely, the randomness that the eigenvalues fluctuate, this improves this bound. What you would expect is that when you believe kind of a priori in this picture, which I showed you before, that there's the semicircle emerging, then the kind of the Stieltjes transform of this density of states, the empirical eigendensity of states, should be close to the Stieltjes transform of the semicircular distribution, which I denote here by this m of z. So no m mu n, but m without this index. This is indeed true in this, which is expressed by a local law, which is down here in this box, when you appropriately test it. So what I do is I look at the difference of the random resolvent and this deterministic Stieltjes transform of the semicircular distribution. I expect this difference to be small, and it's in fact true in these following two senses. If I take the normalized trace against some deterministic matrix A, so it's here, and I assume it to have bounded norm, and deterministic unit vectors x and y. So take this scalar product here. And it is true that they are small by 1 over n eta, where eta is the imaginary part, absolute value of the imaginary part. And this rho here is the pi inverse imaginary part of this Stieltjes transform of the semicircular distribution. And this holds with very high probability up to n to the epsilon factors for any small epsilon. So there could be some conspiracy in the matrix. So for example, if you flip the coin and your matrix is just the one where you always flipped heads and you put always 1. I mean, this matrix will not have eigenvalue distribution, which is close to the semicircle, but this event that all the entries are 1, this is very unlikely. So these are kind of suppressed in these Prec notations, but with very high probability up to these small n to the epsilon factors. The G is close to M in these two topologies. So this is what's called a local law. And my talk will be about local laws and extensions of local laws to various regimes around this classical result of the Wigner semicircle law, local Wigner semicircle law. Let me tell you a bit about how these are usually proven. Kind of the first one, which identified this semicircular distribution, goes back to Wigner when he computed just the moments of these Wigner matrices and found them to be matching with the moments of the semicircular distribution, which is kind of a global thing because you look at all eigenvalues at once. Following proofs were by the Schur complement formula, using that rows and columns, kind of every row is up to this Hermitian symmetry is independent of each other, so you can take minors and then do it by this construction that you prove this law. And more recent proofs of this were by cumulant expansion. So you look at the cumulant of these entries and prove it in this way. The two more recent proofs, these Schur complement and cumulant expansion, they all these proofs rely on two largely decoupled parts. Namely, they analyze the stability of the so-called Dyson equation, which is this equation, the defining equation for the Stieltjes transform of the semicircular, law minus M inverse equals Z plus M. I mean, this you can explicitly solve. It's a quadratic equation for M, and you find that it exactly matches the with the correct sign convention, the Stieltjes transform of the semicircular distribution. And what you also prove, what one also has to prove in these two methods is that the resolvent approximately satisfies such an equation. So minus G inverse is approximately Z plus G. This is a probabilistic step, kind of that you have to control the error. And then you have a deterministic stability step showing that if two quantities satisfy this approximately, approximately the same equation, then actually the two quantities are close to each other. So that's the main idea, that when this holds approximately, then also G is close to M in these two sets. Kind of famous consequences of local laws are the following things, which I list here: delocalization of eigenvectors. So when you look at them in any deterministic basis, they are essentially flat. They're not peaked in any way. Rigidity of eigenvalues. This means that the eigenvalue is close to its location determined by the semicircular law, up to fluctuations of the order at which they should fluctuate at this precise location. And most importantly, universality, essentially proving this bottom picture, which I showed you on the first slide, up to the fact that it's not really the surmise, but something a bit more complicated. And this proof of universality in kind of the general form that without kind of a moment matching condition in parallel development by Tao and Wu goes back to Erdős-Lein, Yau, and Yin, and consists of these following three steps. First is that you prove a local law on optimal scale, so essentially these bounds down to 1 over n. As the next step, because universality means that you have these this picture, this eigenvalue, this essentially Wigner-Surmise. Let me talk about it like this: Wigner-Surmise picture. This can be explicitly computed for the Gaussian ensemble. You can explicit computations on that. And the idea is that you introduce to your random matrix, which has a priori no Gaussian component, a little bit of Gaussianity by running this matrix valued Ornstein-Uhlenbeck flow. Then you find for this random matrix ensemble that it satisfies, has universal behavior. And afterwards, in the third step, you remove this Gaussian component by a so-called green function comparison or GFT theorem, which is a perturbation argument around this say Gaussian divisible matrix with a tiny Gaussian component. So these are the three main steps: that you understand something a priori, your local law. Next, you introduce a bit of Gaussianity to get the answer, and then later remove it and go back to your matrix where you are a priori interested in. Okay, so these are many forewords about these classical Wigner semicircle law. What I will be mostly concerned with are extensions of this law. So generalizations and extensions of this law. You can essentially do it in two columns. So one column would be that you can ask finer questions. So for example, here I list just a few possibilities. What happens if you look at G minus MA for, say, an observable which is traceless? Then you see that the deterministic approximation vanishes identically. Is there some improvement to the fluctuations as well? This you could ask. What happens to multiple resolvents? This is what I will mostly talk about in the next half an hour or so. You can also ask about what happens to local laws if you don't look at the resolvent, but the imaginary part of the resolvent, when you just write it in spectral decomposition, is better localized in the spectrum. So the one is 1 over lambda minus d. The other has the Cauchy kernel distribution, which has better decay. So it's a finer measure. What happens if you don't measure your observable in terms of its operator norm, but you look at normalized Schatten norms, Hilbert-Schmidt norm, or whatever? This is kind of one type of extension you could do. The other one is you look at more general models, not Wigner, but for example, deformations of Wigner. So a deterministic matrix plus Wigner. So you have some deterministic shift in there. You assume not the IID condition, but you have a variance profile or even band matrices. You could look at random graphs, correlated matrices, or you want to understand similar questions for non-Hermitian matrices, which you might want to study by hermetization of them, and also multi-resolvent laws for these. So there are a ton of questions which you could ask. Here I list some people it's not a complete list, who worked in either of these columns. And what is the goal of my talk is to convince you that the strategy, which I haven't told you yet what it is, that it is effective in both of these columns. So in either you ask finer questions or more generalized questions. And I want to convince you that it's powerful, especially for the case of multiple resolvents in both columns. And I will also want to tell you some new results which you obtained by this method. So that's enough of, say, the intro, and gives you a bit of the plan of this talk. Are there any questions? And let's proceed with part one. So multi-resolvent laws. So this kind of alternating chain of resolvent and deterministic matrices, and old proof methods. So they're still quite recent, but superseded by the zigzag. Okay. So the general form of such a law is that you have this alternating chain, and you also want to find concentration estimates around the deterministic object. And the general form is that, okay, the good old operator norm here of all these k deterministic matrices AI, and the n eta, 1 over n eta bound degrades to eta to the k. So eta is it's interesting when the eta is small, you want to go down to the real line, get precise information. And that's the general optimal form in this way. You can think about it, say, for this case, when all the a's are identities and all the indices are the same. So you look at g to the kth power of the resolvent, which is essentially the kth derivative of a single resolvent. And then this eta to the k comes about as, say, the kth derivative of the eta. So it degrades with every derivative which you take in these laws. But this should not be taken literally, because so one is not only interested in having identities in between, but any deterministic matrix. And these are not indicated by what I just said, not just a consequence of the single resolvent local law, because although g is close to m, it's not true that g square is close to m square, rather in this derivative fashion, but then only if you put identities in between. But kind of the question you ask is more general and much harder to answer. The mk, so this deterministic approximation, this counterpart to the small m in the Wigner case, this is defined inductively. You can, for the Wigner case, you have explicit forms by free probability theory, and they satisfy such type of bound where suppress these operator norm, which are optimal, kind of in the eta dependence at least. And this is kind of also old, already old, that you can improve this general form in at least, so first in this one way, by the square root of eta rule, which means that if you don't look at a general matrix, which is, so say it has an identity part, but at traceless matrices, then for each traceless matrix, both the size of the m and the error in the local law improve by a square root of eta, which is good in the interesting small eta regime. As an example, let me show you the kind of the 2G law in the most general form in this class. So you have the kind of the tracial mode here, where m1 minus m2, which are the m semicircles of the spectral parameters z1 and z2, belonging to g1 and g2, divided by z1 minus z2. Here you already see that that this can be very, very large. So it can be essentially of order eta when both are complex conjugates of each other, which is this bound. And then you have a better behaved traceless part, where m1 and m2, these are order 1 objects. And this is the local law error. And you have three different terms in terms of eta. One is when both are purely tracial, so identities, then you have 1 over n eta squared. And then here the case where one of them is the traceless one, you gain a square root, and then you gain another square root. And everything is measured in terms of the operator norm here. And you can check what I told you, or we can do it together or pause on it a bit if you're interested. In these two special cases, when AI is the identity, then several terms drop out because the traceless part is 0, or when it is itself traceless, then also several terms drop out. Okay, so this is already one improvement, the square root of eta rule, and a second improvement, which is also known, is that you can improve the operator norm to the Hilbert-Schmidt norm at the cost of replacing some n eta by square root of n eta and so on. And the method I will present to you aims finer on both accounts. On first, the square root of eta rule, we will detect also differences in energies of these two things. Here, it's completely only measured in terms of its traces and operator norms of the traceless part and eta and n, that's it. These are all quantities which appear on the right-hand side. But we also detect some of finer questions and also improve these Hilbert-Schmidt norm dependencies on Schatten norms. And important applications, which for me as kind of a mathematical physicist by heart, are these physics applications, which are eigenstate thermalization hypothesis, ETH, fluctuations around this. So this ETH is known as the QUE in mathematics, in the equipartition principle, pre-thermalization, Low-Schmidt echo. I will not go too much into this, but you feel free to ask me if you're interested in some of them. Okay. So this is one old proof method of multi-resolvent laws. So first note that to understand them, it's first enough to focus on traceless observables, because for the tracial part, I can just use resolvent identity in general to turn a 2G object back in a 1G object in this divided difference structure. So you somehow go down in this hierarchy of chain of resolvents. And this trivially resolves in a kind of a first instability, that G square is like G over eta. And this is this cumulant expansion, which I told you. So we define this underline, which is also called the renormalization, for this reason that if you take the expectation of it in the GUE ensemble, it is 0 identically. So it renormalizes this product to first order even. And then the object you're interested in, G minus M tested against the traceless part here, is this underline with A, and then something which is quadratic in G minus M. So for the purpose of proving something for G minus M, I can neglect this. I expect it to be small. So let me just assume that G minus M against A is essentially this underline. And what I have to do then to prove a local law, a concentration estimate for this guy, is that I have to compute high moments of this underline object. And here I just did the second moment, indicating kind of which intricacies can arise. Namely, what I have to do is I have to maintain these A circs, because they gain me something from the slide before, which I told you, by the square root eta rule. They improve the size. So I cannot just sacrifice them by estimating things by operator norm. I have to keep as many traceless objects as I have there. And at the same time, reduce numbers of G's by resolvent identity, which always give me an eta. And so for maybe here, for the second moment, it still looks quite harmless. But for higher moments, it involves intricate, complicated Feynman diagrams. And it's quite cumbersome to compute this. So this only worked for Wigner, for short chains, so kind of small k, and proving suboptimal bounds. Okay. The next method is what I also was involved in developing further, is the static psi method, which we called it. So this involves kind of is a bit finer question, because you kind of already put in this method what you want to get out. So the target will be that these normalized difference objects, the psi k, so the GA blah 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 minus m, this you will expect by the power counting and the square root eta rule to be something of order 1 over n eta to the k over 2, because I have k traceless resolvents, so I improve it each by the square root thing. So this will be my target to prove that this is order 1. And by the cumulant, minimalistic cumulant expansion technique, so which would mean on this slide before that I don't, that I don't compute high moments of this alone, but I want to compute moments of this, and then I express one of them as this underline, and then which to some people I think is known as Stein's method. I only create kind of I replace one of them, and then the derivative in the cumulant expansion hits this object itself, and it's self-consistent way of doing these kind of expansions. Okay, and what you find by this is if you assume that your big psi k is bounded by small psi k, which is some deterministic control parameter, for the moment it could be anything, satisfies this this system of this system of master inequalities. So you find that your psi k, the object you're interested in, for which you want to find that it's order 1, you find, okay, the 1, and then several terms, so 3 terms, which we'll also see later. So you have one kind of sub-homogeneous term, which involves psi's which have a smaller index than the original one. You have some terms which are homogeneous when you add the indices, but non-linear and suppressed by an n-eta factor. And then something which goes up, has a higher index, but is suppressed by the square root of this object. So everything has at most, when you count the homogeneity in the index, it's at most k. And you have to analyze this nonlinear system of equations and also make sure that it closes, because you would always go up. So for psi k, you would have to understand psi 2k, psi 4k, and so on. You would go off to infinity. And this is done, this closure of kind of this indicated BBGKY hierarchy is by a reduction inequality, which is essentially a Schwarz inequality for traces, that you estimate psi 2k by this n-eta square and the psi k square itself. And in this way, it closes because of the triangular structure. By plugging it in, you first get psi k is n-eta. This you can plug in again and get your target 1 bound. So you have an internal bootstrapping argument in this system of master inequalities. And this worked for arbitrarily long Wigner chains and also for deformed Hermitian and non-Hermitian matrices. So in this sense of column B, which I told you in the beginning. Anyway, both of these methods are superseded by Zigzag, but contain important concepts. For example, that we will again find time-dependent master and reduction inequalities in this new method. Okay, part 2. I will mostly explain this setting for you in the sense of column A, so for the finer questions. And let me tell you what this mysterious zigzag strategy is. Let me draw you a picture why it's called like that. So I draw a diagram in 2 dimensions. On the x-axis, I have the Gaussian component. And here I have the eta, the imaginary part. I want to understand in general a matrix which has very little Gaussian components. So let me write here eta is like 1 over n. Okay, and here eta is 1. So this is kind of my target where I want to understand the matrix. And the idea how I approach this point is that I start from above, from a matrix which has no Gaussian component, and somehow decrease the eta, but introduce a bit of Gaussianity, and then go back in this way, and in some sense bootstrap my way down to my target matrix. And this shape is a zigzag, and this is the name of the strategy. And the 2 steps, so the diagonal going down, but at the cost of introducing some Gaussian component, this is what we call the zig, and the removal of the Gaussian component is what we call zag. So this is the strategy, and it's summarized again on this slide. So here I drew it in many steps, so really zigzag, zigzag, zigzag. In some situations, it's also fine to do only 1 zig and 1 zag. So this is the general picture, and this is kind of the special picture that sometimes you are capable of doing it in this way. Okay, so as I said, there are the 3 steps. So you have to understand your original matrix at a large value of eta. This is what we call global law. So when kind of norm bounds of your matrix are affordable, there's no danger in taking these norm bounds. So you can easily prove these in an independent way, namely that this G minus M object is bounded by 1 over n. Okay, that's fine. That's much easier to do. And then we do a dynamical psi method. So dynamically look at these normalized differences and run 2 flows in parallel. So one flow is that one introduces a bit of Gaussian component, so removes the original matrix and introduces this Gaussian part, and in parallel evolves the spectral parameters, the z of the G, in this form, in this box equation, which is the characteristic equation. And then by Ito, you can want to estimate psi k at t, at your target time, by psi k of 0, and integrate the derivative of this psi k, which you computed by Ito, to gain information about this one. Psi k of 0 is bounded by 1 by the first step, And then you're left with then you have your local law, but for a matrix Gaussian component and down at the target level. And then you have to remove it by, again, similar to the three-step strategy, essentially self-consistent by a GFT, but now in a self-consistent way, because knowing you know the local law for some matrix and you have nothing else, you have to kind of push it forward to the matrix ensemble, which has no Gaussian component. Maybe for the experts, there are two ways how you can do it. Either in a discrete way, you replace one matrix entry by the other in this Lindeberg fashion. This also leads to a discrete Grunwald inequality. Or you do it in a continuous way. You can essentially run the same flow again and find a differential inequality for these psi depending on S. And maybe this blue term as an indicator where why sometimes you need that you run multiple zigzags and not one of them, because this blue term can be very big when eta is small. So when eta is like 1/n, this term is big and you cannot integrate it back in time. So this means, when this exponent a is bigger than 0, this means that if you are at small eta, you have to compensate by small time steps. And this is what I drew here, that when you go down, the time steps have to get smaller and smaller. Okay, so this is maybe more of a technicality. Okay, so I will mostly tell you about the zig part. So this diagonal part, you go down and increase a bit the Gaussian component. So what we look at is GT of ZT, so kind of a you have a time dependence in the matrix and time dependence in the spectral parameter by these two evolution equations, dW of t and dt of Zi of t. Okay, let me show you why this kind of combination of the two effects is kind of what does the magic in this setting. Because when I just take by Ito's lemma, take the derivative of the normalized trace of G of ZT, I get this equation. And what I don't like in this equation is that I have G squared, because G squared, this instability that G squared is like G over eta. So this is a bit prohibitive for proving a good local law. So this blue term is something I don't want to see or should be compensated by a small factor. I could do it naively in the other way as well, that I take the derivative of GT of Z. So only looking at the time dependence of the W of T. Okay, then I get more terms by Ito's formula, also a martingale term here. What I now have is this orange prefactor, GT of Z plus Z of T multiplying this one. This is still not good. This is something order 1. But when I look at this combination GT ZT, then I have, okay, this term is fine. I can just, sorry, this should be a ZT as well. I can just absorb it on the other side by computing the e to the t over 2 of this object, then it wouldn't be there. But then instead of this orange bad guy, I get the green term. And when I plug in my formula for partial derivative of ZT, then I see that this green term exactly evaluates to this difference G minus M. So I have a small prefactor in front of my critical term. And this is the good thing about the zigzag, about the zig flow. So this is what I just said. The characteristic equation ensures that this term is small, which is the key effect. And this shows you this evolution, how it looks like, how spectral parameters evolve under this flow. And here are lists of people who used this characteristic flow in different setups. The upper list for single resolvent question, and the lower list also for multi-resolvent questions. Okay, so let me discuss a few terms briefly, which appear in this flow. So I do it in the multi-resolvent setting, and we focus on the orange and the blue one. So the orange is the martingale term, which plays a crucial role, and here this term, which already indicates that it has some non-linearity in the difference. Here's one difference, and here's another difference. And the art of the game lies in the fact that I have to design good self-consistent mean and standard deviation sizes, which I call MK and SK. So MK is this bound on a deterministic object, modulo in eta. It's just convenient to include this eta in this way. And the standard deviation size I put as this normalizing prefactor in front of my psi k with the target that I want to prove them to be bounded by 1. So psi k, little psi k being 1. And what I need is that these estimates, this is kind of a property of this flow, is that they satisfy this super multiplicativity estimates and this kind of bound, M is bounded by S, and this doubling estimate that M2k is bounded by SK squared. Okay, this will come out. Maybe before I move to the next slide, let me also show you that the green term here as well has this also inherits this key effect of the flow, that there's a g minus m in front of a term where you have more g's than previously. So this is needed here as well. Okay, then let me tell you how two critical terms in this flow are estimated and how you get this sk, how you get your answer, the local law. So the following ingredients are there. First, g squared is like g over eta. Then the ms relations from the slide before, and the integral rule that when I integrate at least in the bulk of the spectrum, not at the edges, so nicely in the close to the center, then the power of eta improves, the inverse power of eta improves by 1 if I integrate it in time. This you can also just check from the characteristic equation. So, and the idea how you get the answer for your multi-resolvent law is that the martingale term, the orange one, which gives the normalization, this n over sk, gives the size, essentially what you can prove by its quadratic variation. So you control this martingale term by the Burkholder-Davis-Gundy inequality in the following way. So this is the quadratic variation indicated here. This bounded by 1 over n squared. When I go back to this one here, I have two normalized traces and this 1 over square root of n, so I get a 1 over n squared, and then a chain which is twice as long and has additional g's. So here in total 2k plus 2 resolvents. So what I get from this one is the following. So I have the 1 over eta s squared from the 2 extra g's. Then I have the eta s from this ansatz. Mka is eta times mk, so this is the upstairs eta. And then it's the bound on the deterministic approximation divided by n squared. On top of that, I have fluctuations of this doubled chain, which again are treated by a reduction inequality, as I told you in the old static psi method. And then by this ansatz, I have the m2k over n squared. This gives me sk over n. And this from this guy, you see it's positive. I mean, it's quadratic variation here. And this dictates me how good of a local law I can prove. And this is what I like to call martingale mantra, so to say. You look at the quadratic variation, you understand this guy, and this tells you how good you can even prove. Okay. And then as another example, let me maybe skip it in interest of time. The nonlinear term, the blue guy, follows by using the same ingredients here. The result of this thing will be time-dependent master inequality without equivalent expansion, just by running this flow. The initial condition is proven by the global law, so this starting point here. And as I told you, the red terms, the 2k fluctuation, are treated again by a reduction to break the infinite hierarchy, the a priori infinite hierarchy. Okay, so this is maybe summarizing just what I just told you. The Zig is the heart of the zigzag strategy. Otherwise, you couldn't go down in this picture. In some sense, it's inspired by a 3-step strategy. You have something a priori, you add a bit GUE to get the answer, and then remove it afterwards. It inherits a double bootstrap. So because you first reduce the eta, which is often called bootstrap in random matrix theory, and a bootstrap inside the master inequalities, that you get weaker bounds, which you feed in to get better bounds. Then the 3 main features, kind of the characteristics ensure this miraculous green cancellation, which I showed you. The quadratic variation of the martingale term dictates what you can prove. And at least for Wigner, which is the setting I showed you here, the art of the game is just to find good mean and standard deviation sizes, these m and s, satisfying these relations. And these allow us to prove better results kind of in terms of the norms of A or including densities in the spectrum. So the outcome of this whole Zig is that you have your desired local law, but with an order 1 Gaussian component, which then, and I will not talk about it in this seminar, remove it by a GFT, okay, in a self-consistent way. Okay. Then I still have 5 minutes to talk about the new results which we obtained. So so remember maybe the 2 columns. Column A was finer questions for Wigner. Column B was generalized models. And I want to tell you some results in both of these columns. First result is a local law for a multi-resolvent local law for imaginary parts of G and traceless observables, AI, so they are traceless. and in the regime where NL is bigger than an epsilon, which is what we call above the scale, because the NL essentially means how many eigenvalues are sitting in an interval of size eta around an energy, which is kind of around the spectral parameter Zi. And this concentrates around this M in this particular form that you pick up all the local densities, and this is particularly interesting at the edges of the spectrum. Then it's optimal in terms of the Hilbert-Schmidt norm of the observables here. And then you have this n factor. That somehow when you agree on the fact that you want to measure it in terms of Hilbert-Schmidt norm and these rows, then this is an optimal bound. And in particular, it allows you for k equal 2. This one is not here, this nk over 2 minus 1. So what you find is that this ImGA object, which allows to control such eigenvector overlaps, which are the central objects in eigenstate thermalization hypothesis, somehow tells you that this is bounded by rho and the Hilbert-Schmidt norm. And catching these two facts simultaneously, that you have the densities, which can be very small at the edges, and the Hilbert-Schmidt norm, which can be much smaller than the operator norm, catching these things simultaneously allows us to, so let me skip this argument, how you obtain, how you do this this follows by spectral decomposition and rigidity of eigenvalues. Anyway, that you get this concentration estimate for these overlaps, that random eigenvectors normalized, two normalized ui, auj become approximately deterministic with this optimal error uniformly in the spectrum. And our achievement here is that we do it uniformly in the spectrum, so we take care of rows, and with the optimal norm of the observable. And previous results did it with operator norm, or only on the bulk, or for special observables. This is this result.
Right, is the reason to use Hilbert-Schmidt is because it's the truth? Or
That's the truth. For GUE, you can compute it, and this is what comes out.
So does this help to actually, can you like compute the fluctuation, say, of the quantity of the second mass?
Yes, yeah, this is Gaussian.
Okay.
Yeah.
But like, does it help to, does your result actually help to compute this fluctuation?
No, so the fluctuations were known already before that, but this was done only in the bulk. We didn't bother to look at the edge in particular. Okay. The next is what I already teased a bit, these Schatten norms. So let me introduce for a positive L, these weighted Schatten norms. So I look Hilbert-Schmidt norm divided by L to the same power, fractional power, which I took off the trace. And here this P Schatten norm. So this combination is what I call the weighted Schatten norm, weighted L Schatten norm. And then what we also proved is that this alternating chain, again, G 1 to K, concentrates around M with this bound here. Okay, and this is for me it's particularly interesting because for the Schatten norms you can gain very much when the observables of low rank, and this is maybe illustrated here. So the blue result is what I have here, and this is optimal. You again computed for the Gaussian case, and this is the truth. And the previous bounds were this one in terms of operator norm and in terms of Hilbert-Schmidt norm. They are also optimal if you agree to only use these norms. So they can saturate. This one can saturate when A is of full rank. This one can saturate when A is of rank 1. But this one is the optimal one and optimally interpolates between these two. So as an example, when well, let's maybe not go into this example where one can check it separately.
This is all for
This is also, yeah, having all moments. Yeah.
It doesn't go beyond Wigner, right?
No, this is only for Wigner. On the next slide, I will tell you something about non-Wigner models. Or on the second next slide, to rush a bit. So the application for this is in thermalization problems. When you're interested in the Heisenberg time evolution governed by this Wigner matrix, you can compute it by residue calculus from the resolvent. And this particular result with optimal Schatten norms allows to study the out-of-time ordered correlator, the OTOC, which is a very important object in quantum chaos. It's defined like this. You take the commutator of the time evolved A with an other observable B, absolute value square, normalized trace, and 1/2 in front for convenience. And then we can rigorously prove kind of such pictures for the OTOC. And that we look at Schatten norms, in particular, extends the physically important accessible times, this T star, which they call scrambling time, which is when the OTOC reaches a maximum value, and the relaxation time, which is when it essentially comes to its stationary value. And here it is plotted in two extreme scenarios. One is A equal B, the black curve, when the rank of A is n to the A. This exhibits a prominent peak, which also was not seen in physics literature before. And the other setting is when the A times B is 0, and then you see the red curve independent of the ranks of these two observables. And this kind of, when you think of the rank modeling locality in these Wigner, in these systems where the Hamiltonian is a Wigner matrix, this is quite interesting to see. Okay, results in column B. Let me maybe be very brief about this. So what we also did recently is when we look at the correlated random matrix, so it's not independent, you can allow for correlations in such a way that the cumulants, they decay, kind of the strength of this cumulant in a summable way. This is essentially the condition. We proved that the eigenvalue statistics at such cusp singularities, here the cusp is, so remember for Wigner, you have seen the spectral edges. Under very general conditions, there's only a second singularity type which can occur, which is the cusp, or a cubic root cusp in a symmetric way. So this is this cusp here. And kind of physical cusp versions of this are here, these small local minima or small gaps over here. And what we proved is for these correlated ensembles, optimal single resolvent law, again with the Hilbert-Schmidt norm here, which by the three-step strategy, which I told you about, prove universality at the cusp singularity, which for this model was the only missing piece. So it was known in the bulk and at the edge, but not at the cusp until now. Why it is so difficult is because the cusp in this stability proof, which I told you about, that kind of the traditional ones always had the stability analysis plus the probabilistic analysis. This has a second order instability. And now what this shows is that Zigzag also is capable of overcoming second order instabilities, not only at the edge for Wigner, where I showed you the ETH result, but also at the cusp. So this is again optimal in Hilbert-Schmidt norm and other dependencies. We also did it below the scale to exclude outliers and so on. Right, and this was previously prohibitive by other methods because the Feynman diagrams could not catch this delicate cancellation, resolving it to second order. Okay, and the final result I want to tell you about is for two differently deformed Wigner matrices. So I look at 2HL with the same Wigner matrix and different deformations. I assume without loss of generality that their trace, the average trace is equal to 0. This just means that they cannot just be drifted apart by a trivial shift, so they stay at the same place. And what we prove is this optimal eigenvector decorrelation effect in the bulk of the spectra. So when I look at two eigenvectors, Ui of L, of the two matrices, and look at this overlap, then it can be small if the deformations are rather far away or the eigenvalues are rather far away. So these are the two effects that either the D's, as I said, the D's are far or the lambdas are far, and these two effects interplay in another term where they are not coming in quadratically but linearly, but in a linear combination which can cancel out. But this is also optimal, this bound. And I told you it supersedes the square root of eta rule because this one also looks at decorrelation effects because of energy distance and deformation distances. So what Zigzag does here to get this law is prove an IMG1, IMG2, where 1 and 2 are kind of also with different deformations, a bound and local law for this object in terms of the gamma, which is here the full denominator. Right. So is it also capable of doing something for random matrices in two different spectral families? And we also have this ETH-like decomposition. So when you look at it with the deterministic matrix in between, this factorization that there's kind of something deterministic and the bare eigenvector overlap and an optimal error modulo. Okay, no. these are kind of all the things I talked about. These are the Zigzag papers, and these are some other things which I mentioned on the side. So let me quickly summarize. In part one, I told you about multi-resolvent laws, the three proof methods: cumulant expansion, static psi, static normalized differences, and dynamical psi method. Then in part two, I told you that the Zigzag is is a powerful tool, quite versatile in applying it to various settings. And it effectively handles instabilities. So this G square is G over eta, or the edge and cusp singularities. It contains a double bootstrap, namely in going down in eta here, and then internally in these master inequalities. And removing the Gaussian component is done by a self-consistent GFT via Grunwald inequalities, either in discrete or continuous way. It has various applications to different problems. For me, most interesting mathematical physics, for ETH at the edge, long-time behavior of Ottok, correlated cusp universality, and this eigenvector decorrelation effect. Yeah, and I hope to have convinced you that it's effective in both of these ways, how you can generalize it. And that's it. Thanks.
I have one question. Did you see if you can do anything for heavy tail matrices at all with this?
No, not yet. I think, I mean, I think I don't quite know if for heavy tail matrices you also have such good some of the estimates in the Prec sense, or it's a bit weaker that you control, I don't know, finite moments of these matrices. I'm not so sure, because this is all kind of designed for this class that you have finite moments to order. But it would be interesting to look at for sure.
And then did you get like the optimal efficient on decay of correlations in the correlated case?
Sorry. So it can surely be weakened a bit. Somehow morally it is that it's summable, so it's L1 summable. But for lower order cumulants, I don't know, for cumulants of order 3 and 4, you have to impose certain combinations of indices that they are summable in a particular way. But somehow the precise structure of this cumulant decay only comes in the GFT part. The Zig part is completely agnostic to this. You just run the usual semicircular flow, but then in the GFT you have to run the modified one, which has a correlated Brownian motion, and then you see these things. But they are very similar, apart from something which is needed to handle the Hilbert-Schmidt norm, which was also not done in any previous paper, to the cumulant decay assumptions which were there for the bulk and edge local laws in this setting. So.
Any other questions? All right, let's thank Josh again. Josh. This was my first time.
Hi. Hi,
Yeah.
Yoshi. Nice to meet you.
It's good.
Good.
Visiting Phil
Yeah.
next week.
How do you choose the number of decks?
It also depends a bit. So it's usually
Hi.
Yeah, yeah. Hi.
Nice
Yes,
to meet
yeah,
you.
yeah. Nice to meet you too.
For the talk.
Yeah.
Together around this.
Yeah.
Thanks again.
Yeah. Thanks. So in some, I think it's like you do it in such a way that you have in these local laws and these Prec bounds, you have some n to the epsilon, some tolerance exponent, and then the number of zigzags, it's I think log of epsilon.
So what's the restriction to choose the instant one that you have a multiple deck?
Yeah. So one example would be what I showed you. So all these restrictions come from the Zag, essentially. So I showed you this DDS of expectation of psi s p, and then there was the 1 plus 1 over square root n eta to the a, and you have to make sure that, because so let's say we are in the bulk, let's say, and then in this